Dear students, today's topic is polarization of light. Light can be categorized in two different categories. One is unpolarized light and other is polarized light. An unpolarized light can be defined as when a light wave vibrates more than one plane, whereas a polarized light can be defined as when a light wave vibrates only one plane. So, what is polarization? Polarization is a process of transforming unpolarized light into polarized light. Now we discuss an experiment on polarization. Let us consider an ordinary light falls on transparent hexagonal shape of tourmaline crystal, which is acting as a polarizer. Light passes out from another crystal, which is acting as an analyzer only when optic axes of polarizer and analyzer are parallel to each other. In the next step, light falls on polarizer. It does not pass out from analyzer only when optic axes of polarizer and analyzer are perpendicular to each other. This experiment concludes that light wave is a transverse in nature. In the previous slide, we mentioned polarizer and analyzer. But what are they? If an optical device can restrict the vibration of any unpolarized light in a single direction, then it is called polarizer. Whereas when an optical device can indicate whether light is polarized or unpolarized, then it is called an analyzer. Basically, there is no difference between polarizer and analyzer. They are given different names due to their different role in optics. Now, the pictorial representation of polarized light. Usually, a plane polarized light vibrates in the plane of the paper and they are represented by a straight arrow. This is the straight arrow. When the vibration of polarized light are perpendicular to the plane of the paper, they are represented by dots. In this slide, we discuss about the classification of polarized light. There are three types of polarized light. Firstly, plane polarized light. Secondly, elliptically polarized light. And lastly, circularly polarized light. In case of plane polarized light, the orientation remains fixed, but its magnitude changes during vibration. The orientation and magnitude of light waves vary continuously in case of elliptically polarized light. On the other hand, when the magnitude of light vectors remains same, but the orientation changes continuously, it is known as circularly polarized light. Now we discuss about the methods of producing plane polarized light. There is three methods. One is polarization by reflection. Secondly, polarization by refraction. And lastly, polarization by double refraction. If a beam of ordinary light is incident on partially reflecting transparent medium such as glass, the reflected beam is partially plane polarized. The degree of polarization depends upon the angle of incidence. Now, we focus on the polarization by reflection. Two things are very important. One is Brewster's angle or angle of polarization, which is denoted by IB. Here is a IB. And other is Brewster's law. Let us consider an unpolarized light fall on reflecting transparent medium and the light rays reflected as well as refracted. But when the angle between reflected and refracted ray is 90 degrees, reflected ray is completely polarized. Then the angle of incidence is known as angle of polarization or Brewster's angle. Let us consider the unpolarized light incident on a medium of refractive index mu. Then Brewster's law states that mu is equal to tan IB. Now we prove mu is equal to tan IB. Let us consider an unpolarized light incident on a medium of refractive index mu. Here there is a refractive index to media and the refractive index is mu. AO is the unpolarized light incident ray. Unpolarized incident ray, AO. This is the unpolarized incident ray. OB is the reflected light which are totally polarized. And OC, this is OC is a refracted ray. So, in this figure, AO is the incident ray which is unpolarized. OB is polarized reflected ray and this is OC is the refracted ray. So, from the figure, we say that BOY plus YOC is equal to 90 degree because the refracted ray is completely polarized. Using the Snell's law, we can say that mu is equal to sin I by sin R. I is the incident angle and R is the refracted angle. When I is equal to IB, then R must be equal to, when I is equal to IB, R must be equal to 90 degree minus IB. So we replace the R, we get sin IB by cos IB, which is tan IB. So we can prove that mu is equal to tan IB, which is the Brewster's law. Now we discuss about Molas law. It states that when a beam of plain polarized light is incident on an analyzer, the intensity I of light transmitted from the analyzer varies directly as the square of the cosine of the angle theta between the plane of transmission of analyzer and the polarizer. Now let A be the amplitude of the plane polarized light and theta the angle between the plane of transmission of the analyzer and the polarizer. Now the amplitude A of the plane polarized light emerging from the polarizer may be resolved into two components. One is A cos theta, which is along the plane of the transmission. Another is A sin theta, which is perpendicular to the plane of the transmission. The component of A sin theta is reflected from the analyzer, whereas the component A cos theta is transmitted through analyzer. Therefore, the intensity of the transmitted ray is equal to I proportional to A square cos square theta. That means I is equal to I0 cos square theta. This is known as Molas law. So, varying the angle of theta, we get different intensity. Now, we discuss about double refraction. When an unpolarized light is incident on an anisotropic crystal, the incident light is split up into two reflected planes polarized rays. One is extraordinary ray, that is known as E ray, and other is ordinary ray, O ray. This phenomena is known as double refraction. So, what do you mean by E ray and O ray? The refracted ray, which obeys the ordinary Snell's law of refraction and having vibrations perpendicular to the principal sections of the crystal, is known as ordinary light or ordinary ray O ray, whereas the refracted ray, which does not obey the ordinary Snell's law of refraction and having vibration along the principal section of the crystal, is known as extraordinary ray or E ray. Several times we use the term polarizer and analyzer. Nickel prism is an optical device that can produce plain polarized E ray from unpolarized light and have ability to analyze the plain polarized light. It can be used as polarizer as well as analyzer. Now the question is, what is the principle? The activity is based on the principle of double refraction in an uniaxial crystal. By the process of total internal reflection, the O ray is eliminated and E ray is transmitted through this crystal as a plain polarized light. Last one is polarization by scattering. When an unpolarized light is passed through a medium consisting of small ultra microscopic particles, the light is scattered and the scattered light is found to be partially polarized. The degree of polarization is maximum for light scattered in a direction at right angles to the original beam. Here we give a practical example of polarization by scattering. We see the blue sky during the daytime, whereas the sky appears red in color during the sunrise and sunset. Why? The explanation is, we know the intensity of the scattered light is inversely proportional to the fourth power of the wavelength. That implies light of smaller wavelength is scattered more than longer wavelength. When white light falls on the dust particles or molecules of the atmosphere, blue color of light is scattered more than red color of the light. So it appears the sky is blue. On the other hand, light from the sun has to travel much more longer distance to reach our eye. Large portion of blue color of light is scattered sidewise, and blue color is removed and red color is prominent. So sky appears red during the sunrise and sunset. Lastly, when sun is higher in the sky, the sunlight travels relatively small distance of atmosphere to reach us. Only small fraction of incident sunlight will be scattered, and that's why sky appears white during noon. Lastly, the application of polarization of light. Polarizers are used in sunglasses. Secondly, polarized light is used in photoelectric trace analysis. This polarized light is also useful to determine size and shape of the viruses. Lastly, polarized light finds many practical applications in industry and in engineering science. So, thank you.